into the universe with the right equipment and you will hear it humming no matter where you look in the sky. Of course, it's not possible for sound to travel in the vacuum of space. Instead, we are talking about the hum of gravitational waves. You might already be familiar with a similar signal discovered decades ago. It's called the cosmic microwave background, and it is the afterglow of the Big Bang. This glow of microwave light was a groundbreaking discovery. It was the smoking gun that solidified the Big Bang's place as the leading theory of our universe's beginning. Yet, this light signal had a glaring weakness. Despite it being the earliest light of our universe, it was emitted almost 400,000 years after the Big Bang. If we want to go back earlier, we will need a background signal made not of light, but of the ripples of the fabric of space-time. In 2023, astronomers at the Nanograv collaboration have announced that by using a clever trick, they may have detected just that. Using exotic stars as a galactic-sized gravitational wave detector, they measured the faint hum of space-time itself. This hum of gravitational waves might just be the reverberations of the very creation of our universe. We covered the LIGO detector and how it uses lasers to precisely measure the minuscule changes in the length of a tunnel caused by gravitational waves passing through. These gravitational waves stretch and squish space-time, causing changes in the time it takes for light to travel from one end of the tunnel to the other. But detectors like LIGO are only sensitive to a specific kind of gravitational waves. Like light waves and sound waves, gravitational waves can come in different frequencies, and LIGO is only able to listen in to one part of this spectrum, the high frequencies. That's when these binaries are spiraling in on each other rapidly, completing hundreds of rotations per second before colliding in a great bang. But that is also why LIGO cannot listen in on the much earlier stages of these binaries, when the objects are orbiting each other at a much greater distance. Because these orbits are much slower, the gravitational waves they produce are of a lower frequency and energy. So you could say, rather than a great bang, they give off a faint hum, combining into one collective signal. Bigger black holes give greater contributions to this signal. The loudest contributors would consist of pairs of supermassive black holes, the kind you'd find at the center of galaxies. These binaries, which consist of black holes billions of times the mass of our Sun, are found at the center of galaxies. These binaries, which consist of black holes billions of times the mass of our Sun, are expected to be rare because they only form when something truly spectacular happens, the merger of two galaxies. When galaxies merge, because of the vast amounts of empty interstellar space in them, they mostly phase through each other. Very few, if any, actual collisions of stars or planets happen. But the stars gravitationally attract one another and merge into one collective galaxy. And the nuclei of these galaxies, the supermassive black holes, form binaries that continue orbiting one another long after the galaxy merger appears to be complete. It's these remnants of galaxy mergers that we would hear most strongly in the ultra-low frequency range, specifically around the nanohertz range. Yet, just like how the human ear cannot hear sounds with ultra-low frequencies, LIGO is deaf to this cosmic cacophony. If we could listen in, we would gain new insight into galaxy mergers and black holes. But that's not all. One of the most exciting things about the gravitational wave background is that it is a window to the very first moments of our universe's existence. Let's quickly recap what we know about the cosmic microwave background. This microwave light is the earliest light that we can detect because for the first 400,000 years, the universe was opaque to light. What does it mean for the universe to be opaque? Initially, the universe was far too hot for neutral matter to exist. Electrons and protons were unable to bind together and form neutral atoms, simply because they had too much energy. This state of matter is called plasma, the same stuff that stars are made of, and the universe was filled with it. Light gets trapped in plasma, unable to move through space without bumping into the charged electrons and protons, being continuously absorbed and emitted. But once the universe expanded and cooled down enough for the protons and electrons to coalesce into neutral hydrogen and helium atoms, it suddenly became transparent. The light was finally freed. This light was then stretched by the expansion of the universe until it redshifted into microwave light. This is why the cosmic microwave background is the earliest light of the universe. But gravitational waves are not made of light. They are made of space-time itself. Plasma is no obstacle to them. To gravitational waves, the universe has been transparent from almost the very instant of the Big Bang itself. They can penetrate past this plasma barrier and offer us a glimpse of the very first moments of the universe's creation. Because these primordial gravitational waves have been traveling for so long, even if they were originally produced with a high frequency, they would be greatly stretched by the expansion of space-time. They would be redshifted into ultra-low frequency gravitational waves, the same kind that would come from black hole binaries. Together, these multiple sources will give us a so-called stochastic gravitational wave background existing over a range of low frequencies. How can astronomers retrieve this treasure trove of information? How can astronomers retrieve this treasure trove of information about black holes, the Big Bang, and more? Can we build a better LIGO and detect how the Earth is bobbing up and down in these gargantuan gravitational waves? Well, LIGO works by sending two beams of light being sent along perpendicular tunnel arms. The beams are reflected by mirrors at the ends of each of those tunnels, and they return to the starting point and are compared with each other. This is so that if space-time gets distorted along one direction, the information from the other direction can be used to get a sense of how much it has changed. Unfortunately, if we were to design a new LIGO to detect these gravitational waves, we would need to have tunnel arms that are much larger than anything we could build on Earth. This is because the frequency of a wave is inversely proportional to its wavelength. Ultra-low frequency waves have an ultra-long wavelength and would require us to look at changes over a much greater distance to notice the effects of these gravitational waves. For nanohertz waves, that is, one full fluctuation taking a billion seconds, a quick calculation, wavelength equals speed of wave over frequency, tells us that the wavelength would be around 10 to the power 17 meters. For a sense of scale, the distance between the Earth and the Sun, or an astronomical unit, is 10 to the power 11 meters. A light year is around 10 to the power 16 meters. The wavelengths we are discussing are tens of light years long. Clearly, we cannot build anything suitable for this task on Earth, or even in the solar system. We need to go beyond our stellar neighborhood. But rather than wait for humanity to ascend beyond the confines of our solar system and become a spacefaring civilization, astronomers at Nanograv have used a clever trick. You may recall our recent episode on pulsars and how we discussed that these ultra-dense neutron stars are able to spin with remarkable stability, light along their poles, and we can detect the pulses that we receive as those vast beams of light swoop around and hit the Earth again and again. These pulses come with such precise certainty that they are used as clocks of the cosmos, able to keep time across vast distances. Therefore, we can use already identified pulsars to supply us with reliable signals from thousands of light years away. The pulsars are like the mirrors at the end of the LIGO arms, but rather than sending us back a signal we send across, they are generating their own. Nanograv have cleverly concocted an imaginary interferometer that stretches for thousands of light years, and all we need to use it are the good old radio telescopes that we've been using for decades. but our calculations will only be as good as our observations. When choosing pulsars to observe, we need to make sure that they are suitable for the task. The best candidates are handpicked and added to a group called a pulsar timing array. For nanograv, they have made use of 68 pulsars, which were chosen for the following special properties. They had to be spread all across the sky, so we can figure out how these massive gravitational waves are affecting space-time in all directions. Also, they had to be millisecond pulsars, which means they complete millions of rotations per second. In our recent pulsar video, we talked about how these fast spinning pulsars are expected to be the most stable and dependable when it comes to the regularity of their pulses. In fact, their stability even rivals that of some atomic clocks. We could not ask for better timekeepers to be dotted across space and time. This regularity means that we can take measurements of the time their pulses arrive and continue taking these measurements over multiple years to see if there are any changes happening. Of course, the times of arrival can vary due to all sorts of factors, such as the change in distance between the Earth and the pulsar, as both objects continue moving around space, but we can take this into account quite easily. However, there are less predictable factors, such as random fluctuations in the interstellar gas the light is traveling through, causing delays that aren't coming from the stretching of space-time. How do we get rid of the random noise in our data from pulsars located thousands of light years away? With statistics, we can isolate the gravitational wave background from the random noise by considering correlations between pairs of pulsars in the pulsar timing array. Just like LIGO, one tunnel isn't sufficient. We need 2 pulsars on each end of our imaginary tunnels. If similar fluctuations show up with 2 pulsars, it is unlikely that the random noise aligned in such a way to make it appear, by chance, that they are acting in unison. It is far more likely that there is a common cause underlying both those fluctuations, such as the possibility that the photons from the 2 pulsars are riding the same gravitational wave that are washing by them both. We can then relate these correlations of pulsar pairs with their angular distance in the sky. If there is no gravitational wave background, we expect there to be no correlation, and the graph to show a straight line at 0. However, if the data shows a special curve called a Hellings and Downs curve, that would indicate that a gravitational wave background is responsible for the variances. That's what nanograv have succeeded in doing. On the 28th of June 2023, based on over 15 years of continuous observations of their 68 pulsars, they announced strong evidence for the gravitational wave background. This is the graph we've been waiting for. This is a hallmark of gravitational waves, which stretch along one direction and squish in the perpendicular direction. This is exactly what we are seeing with this graph. When pulsars are separated at right angles, their photons are experiencing an opposing effect as they travel to Earth. The error bars in the data appear quite large, but the researchers have calculated that the data shows that the existence of a gravitational wave background is statistically significant at the 3 sigma level. This means that there's only a 1 in 1,000 chance that this is a false alarm and that this data was the result of mere chance. In physics, the 5 sigma level is considered the gold standard for a discovery, but 3 sigma is still very strong evidence. As they collect and analyze more data, astronomers will be able to reduce those error bars and finally announce an official discovery. So, what secrets does this gravitational wave background reveal? While we cannot pick apart the sources of the collective noise just yet, we hope that these techniques will eventually allow us to listen in to specific supermassive black hole binaries and figure out what the signal can tell us about the creation of the universe. Until then, astronomers will continue to use their galaxy-sized detector to calculate how we are bobbing up and down in the turbulent sea of space-time. Have you heard about nanograv before? What secrets do you think gravitational waves could reveal? Let us know in the comments below.